In this video, I'm going to explain comprehensively different types of logistic regression, in addition to discussing all the assumption check considerations that we need to consider before running the analysis. And also, I have some tips about how to report the results. And also, at the end of the main analysis, I also will discuss some strategies to include covariates, if you like to include covariates in your analysis. So the first thing before starting the logistic regression of any type, we need to check the assumptions. There are a few assumptions, like most of the assumptions except one is applicable to all types of logistic regression, disregarding which type you want to test. So this common assumption, the first one is that your dependent variable should be a categorical variable. However, this assumption can have a little bit differences across different types of logistic regression. For example, if you are using binary logistic regression, your categorical variable should have two levels. Like, for example, this version of my categorical variable that has non-clinical and clinical levels of depression. So this is just two levels. So that means that this is very suitable outcome variable for binary logistic regression. However, if I wanted to do ordinal or multinomial logistic regression, then the assumption is that in addition to be categorical, my dependent variable, in addition to be categorical, it also should be also should have more than two levels. That means that, for example, this version of my dependent variable, that is like levels of depression, but including more than two levels, that is mild, normal, severe, and extremely severe. And so when I have a dependent variable like this that is categorical, but its categories are more than two levels, then this variable is suitable for ordinal logistic regression or multinomial logistic regression. However, again, it's matters that whether it's an ordinal variable, categorical variable, or is a nominal categorical variable. And it can be considered as, and be suitable for ordinal logistic regression if there is a natural order between the levels of my categorical variable. For example, I can say that mild is higher than normal and severe is higher than mild and extremely severe is higher than severe. So there is a natural order between, I can consider at least a natural order between these levels. So that means that in this case, maybe ordinal logistic regression can be preferred to multinomial logistic regression. And that's why we call that one ordinal, the other one multinomial, because it's just about the nature of my dependent variable, which is an ordinal categorical variable or a multinomial categorical variable. So, but in general, what we can say in general that can be applicable to all types of logistic regression is that our dependent variable should always be categorical. So that is the first assumption. The second assumption is lack of multicollinearity. And that is like, for example, like here, we have now four independent variables or four continuous predictors in our data set. Lack of multicollinearity means that they should not have very strong correlation with each other. It's okay if they can strongly predict a dependent variable, but they should not be strongly correlated with each other. And there are two ways to investigate that. Like some analysis, like especially not in SPSS actually, some analysis in other software like JASP can give you some measures. The main analysis of logistic regression can also check that if there is a multicollinearity between your independent variables. But in SPSS, at least like in the version that I have, it doesn't have that option. So if you want to check that the lack of multicollinearity assumption is met, the simplest way is to run bivariate correlations between your independent variable. That I explained that in another video. If you check the bivariate correlation video, you can just simply use the option of bivariate correlations, and then you can set all of your variables or just independent variables and then see that if they are highly correlated or not. So in general, if the bivariate correlations between our independent variables is not higher than 0.70, that means that is okay. That means that there is no concern with multicollinearity. But for example, if my IV1 is correlated with IV4 for like 80%. So that is a very large correlation. So that may show that there are some concern with multicollinearity. In that cases, you may not want to include IV1 and IV4 together in a single model. Maybe you want to test your models once with IV1 and once with IV4, but not all together because they are highly correlated and it can show that there is multicollinearity between them. But usually we don't have this problem, especially in psychological research. We don't have really that high level of correlations between two different concepts. So that's the second assumption, lack of multicollinearity, that you can, in SPSS, you can easily check it with bivariate correlations between your IVs. The other variable is independence of observations. The assumption of independence of observation, that is very similar to what you have for other types of regression analysis. This assumption means that there is no uh, there is no duplication, for example, for your data. Like one participant should not have more than one data in your data set. Unfortunately, for this type of, I know that some other types of regression analysis can have some statistical measures to test this assumption, like in addition to visual inspection or checking for duplicates and stuff like that. But for logistic regression, we don't have any statistical measure to test this assumption. So, however, if, for example, in the process of data collection and data cleaning, you have some strategies to check and double check that each participant only has one data point in the data set, that means that this assumption is met. So we can say that this assumption, there is no concern with this assumption. For example, if for the process of data collection, you use platforms like Prolific, usually such platform can safeguard this assumption because they limit each participant to participate only once in the survey. So we also, in addition to like mentioning these measures that can safeguard, beforehand can safeguard this assumption, we also can visually inspect the data, like during the data cleaning process to make sure that there is no duplication. So as long as we are sure that no participant has more than one data point in our data set, we don't have to be worried about the assumption of independence. And the next assumption, this is the final common assumptions among all types of logistic regression, and that is logit linearity, what we call that the assumption of logit linearity. So, and this assumption is a little bit more complex to be checked compared to other assumptions. In general, in a very simple language, this assumption is similar to the assumption of linearity for simple regression, but within the context of logistic regression. So because our outcome variable here is categorical, a simple linearity test does not apply here. So we need to do some transformation in our continuous predictors to be able to check linearity assumption for the context of logistic regression. So this can be done through a method that we call it box Tidwell check. You don't have to necessarily report to this method. You can just say that, like for example, you can just explain the process through which you mention that, but you can see in some textbooks, this method is called as boxed well check. So how to do that? So the first thing we need to do, like in SPSS, we can use the transform option to to do the transformations that we need to check this assumption. If you go to transform and then going to compute variable, and here we need to create a new variable for each of, like a transform version of our independent variables or continuous predictors. We only do that for our continuous predictors. And in this data set, we only have continuous predictors. So that means that we need to do that for all of our IVs or all of our predictors. So you can name it anything that you want, but I like would prefer to name it. For example, I want to create that for my IV4, and I want to create name this new variable like IV4 uh, in, that means interaction, IV4, like the interaction of IV4 with interaction like with sorry. I can say that I use the in and IV4, like the same name of the variable, to show actually that, to understand that this is an interaction term that I'm creating. And then I send, like if I double click on that, I send my IV4, like the variable that, independent variable that I want to make an interaction term for. And then I want to see the interaction of this variable with the natural logarithm of this variable. That if I click on all here, and here I search for ln, that is the natural log. If I double click on that, you see that it's a question mark here. And in this question mark, I send the same variable that I included here, that is IV4. So I double click on IV4 and I send that. So this is actually the rationale of what we are making here. We are creating interaction between a continuous variable with the natural log of the same variable. So we need this variable, this new variable, that we call it like interaction term, to test the assumption that we need here, that is logit, linearity. So everything is okay. Just check that these are the same variables here. Then you can click on OK. And if you check your columns, you can see that now I have this new variable here. So you should do that for each of your independent variables, each of your continuous independent variables separately. So to save time, I did it beforehand for my IV1, 2, and 3, and I just left the IV4 to do it now to show you how to do this. So after that, you created this process for all of your IVs. Then you run the analysis that you want to run, but this is not your main analysis. You just quickly run that analysis to check for this assumption. So, uh, for example, imagine that I want to check this assumption for binary logistic regression. So I quickly go to main analysis for that. I explain these steps later, but I want to quickly run the analysis to show you how to check just this assumption. So I go to regression, I go to binary logistic regression. So imagine that my DV is like here, the binary level of depression, that I put it in DV. And imagine that my main like IVs that are these ones. But here I'm not interested in checking my main analysis. I'm interested to check the logit linearity assumption. So here I send these new variables that I call them interaction terms, that are interaction terms for each of my IVs. I put all of them also in as predictors here. that predictors in this type of analysis also name covariate, but it doesn't mean the typical concept of covariate necessarily. Covariate here means that predictors that can be either your main predictors or covariates. So here, so you see that every continuous variable that I want to include in my main analysis, I include them. But in addition to that, I also include the interaction term for each of my main predictors. And I don't need to set anything here because this is not my main analysis. This is just to check the assumption of logit linearity. So I click on OK. Again, I don't need to check any of the results here because my main analysis will be different when I try them without interaction terms. What I'm interested to is that if I go to block one analysis, and under block one, I'm looking for the table that is called variables in the equation. And here I'm just interested to check the significance of like this column, the significance for the interaction terms, not for my main variables, for interaction terms. So I can say that the assumption of logit linearity is okay, is met for my analysis, for my data, if none of the interaction terms here are significant. So I can see that for the first interaction term is above 0.5, is not significant. For the second one is not significant. For the third and fourth one also is not significant. So it's exactly what I ideally expect. So I can now confidently say that the assumption of logit linearity is met for my data. However, I leave this output here. I don't refer to that because my main analysis would be different if I don't include these interaction terms in my model. So that means that I need to run my analysis again if I wanted to do that. So let me show that for other types of logistic regression. For example, if I don't want to do binary logistic regression, if I want to do that ordinal logistic regression, again, everything would be the same. I just put my dependent variable here, that is like the ordinal version of depression. And I put all of my IVs in like covariates because they are continuous. I put it in the covariate function. And then I put all of the interaction terms also after them. And if I click on OK, again, I'm not interested to any of these results. I'm just interested to check the significance in the parameter estimate, the significance for my interaction terms. So here, for example, you see that for the binary logistic regression, I could say that it was met. But for the ordinal logistic regression, I see that I have some problems with one of my one of my variables. So in this case, if it is not met, one measure that you can consider is to transform this variable and then follow all the and then create an interaction term for the transform version of your data instead of the original version of your data, and then check this assumption. Usually transforming your data can fix these issues. And I have explained how to transform your data in another video, so I may not go through that now. And now let's see, also quickly check this assumption if you want to do multinomial logistic regression. Again, everything is the same. You've put your dependent variable here, your continuous IVs, you send them in the covariate like, because they are continuous. And in addition to that, you also send your interaction terms after that. And you click on OK. So again, in the parameter estimate for each levels of your DV, you just check the significance for interaction terms. So you see that this is are all okay for the normal level. Again, interaction terms significance are all okay for mild level. And the interaction terms significance are all okay because not significant for multinomial level. And they are all okay for the severe level as well. Also, if it's okay here, I would say that maybe you can, I mean, in a lenient, based on a lenient approach, you can then ignore that one of them was significant actually for ordinal one, because ordinal and multinomial one are very similar in the scope, but multinomial also actually is more specific than ordinal logistic regressions. And I will explain the main analysis quickly. So in this case, I can say that yes, the assumption of logit linearity is met, and I can move forward with my main analysis. I'm just checking my note if I to see that I have not to make sure I have not missed any point that I wanted to discuss about the assumptions. And yes, and the final point I wanted to say is that how to report that. Like if you want to report that this assumption is met in your document in a brief way, you don't have to explain all this detailed process. You can simply say that the linearity of the logit for the continuous predictors was assessed using Box-Tidwell transformation. The interaction terms were not statistically significant, indicating no evidence of violating the logit linearity assumption. So this can be as general as this, doesn't need to be uh, detailed discussions for each of your variables. I also, before going to the main analysis, I also wanted to clarify that for the assumptions that I discussed now, they are the only assumptions you need to check for any type of logistic regression. That means that other assumptions that you usually hear about other like types of regression, like for example, normality of residuals or like assumptions like that, you usually don't need to care about them for logistic regression. I just may, yes, except for just one, I forgot to address one. Just the final one that you may consider, maybe not all the textbook consider as an assumption, but some textbook refer to that as an assumption. That is lack of influential outliers. Actually, that is also one additional assumption if you want to run logistic regression. So if you are using binary logistic regression, this assumption can be checked with running the main analysis. When you run the main analysis, there is an option that you tick and it can actually check for you the assumption of influential outliers, and that is through Cox distance. That I will explain this step later when I run the analysis. However, if you are using ordinal or multinomial logistic regression, you need to use the descriptive analysis function that I explained in another video, in the video called Descriptive Statistics and Bivariate Correlation. In that video, you can see that how you can check the influential outliers just based on the descriptive statistics function. So that is also an alternative when you don't have this option included in your main analysis of regression analysis. So that's all. Like you just the first assumption, just an overview of that. The first assumption you need to check is that your dependent variable is categorical. You want to make sure that there is no multicollinearity, no high multicollinearity between your IVs. You want to make sure that there is no influential outliers, and you want to make sure that the independence of observations is met by like some strategies that I mentioned. And you want also to check the logit linearity assumptions based on the Box-Tidwell method that I just explained. And just a final note that these assumptions are very comprehensive and you don't need any further assumptions for logistic regression, except for when you want to run ordinal logistic regression. There is an additional assumption for ordinal logistic regression, which is called proportional odds or parallel lines assumption. And this is only for ordinal logistic regression, and this is focused on assuming a natural ordinal order in the levels of our categorical outcome variable. So we want some sort of consistency in prediction across different levels of our ordinal outcome variables. Like for example, when we have a variable like this that have more than two levels and has an ordinal order between the levels. And but it's a very easy way to test this assumption and can be test just be ticking an option when you run the main analysis. So, and I will explain that when I go through the details of ordinal logistic regression. So, this is nothing it's nothing complex at all. So that was all about the assumption. And